This here, I know is a very poor approximation, is planet Earth. If I take this pen and I point to it, what will happen? I'm trying to point someone on a location on a planet. Come on. Who's with me this morning? Am I pointing to United States or in the middle of the Pacific? The probability to land in the water is like, you can calculate that, right? Nobody's here this morning. Wake up. Okay. Let's pretend I didn't land in the water, and I go to a landmass and I point to it. The probability of finding a person who has no idea what neutrons are, who has never heard of neutron scattering, who will never step foot in a large-scale facility like NIST, or a better one, Oak Ridge National Lab, who will never see a wonderful, complicated, and God, so extremely loud spectrometer as a neutron spin echo spectrometer in their entire life. It's almost one. So think about it. And I will not say from the 8 billion population, but the 320-something or 50-something million United States citizens. You are, how many? We have 20?
One.
Wow. Don't you feel incredibly lucky? Huh? What do you think? What are the chances for you 20 people out of 8 billion to be here? I think you're extremely lucky. So regardless if you're ever going to use this in your entire life from now on, or if you ever remember any of us here, I want you to let this sink for a fraction of a second. Realize that you have to, you must be grateful for this. And not to mention it's for free. You make sure you fund them for
We try to do our best.
So the last thing I will ask from you today, you can all go away and don't have presentations. Don't get intimidated by the committee. But the thing that I'm asking from you today is to give a big round of applause to people that made this possible. Thank you. Antonio, Nishi, Yoon, Norm, Todd, everyone who's here. Thank you, Laura. Okay. Thank you for being here. Thank you for having us. You are incredibly lucky, wherever your road gives you. Luck is a quantifiable measure. I should take advantage of it, because you're lucky. All right, I'm done. You can go back to your laptops, play some whatever Pokemon. Feed the dragons, like Piotr is always telling me. Every time I'm on my phone, Piotr is saying, are you feeding the dragons again? Yeah, because I used to have a dragon game. All right. Neutron spin echo spectrometer at SNS. It might not be of a very, I don't know, interest to you, since you are not neutron spin echo users yet, but who knows, 2 years from now, I have already identified some people that might take advantage of this science. A bit of propaganda. We are at the US epicenter of all the neutron scattering life in this universe. We have 2 big facilities, the Spallation neutron source and HIFER, high flux isotope reactor. There are a lot of instruments at both of these facilities. And there are, well, the SNS is the most powerful. A high flux isotope reactor, it depends how you look at it, right, if you compare it with ILS. Still, if you go to neutrons ORNL.gov, you can read about all this instrument. They have a lot of web pages, the same like NIST page. I don't know if you checked it out. You can look at the instrument, see the science that they're doing, see the instrument team and all that. Every facility in the world has this. We do a lot of biological research, from femtoseconds to microsecond, nanosecond. And atomic to nano and mesoscale. These are some of the spectrometers and diffractometers we have at Spinnaco at the spallation source. And HIFER, as I said, NSE is the top of the line, the limousine. In my opinion, in my humble opinion, this is almost everything you need to remember about Spinnaco. So I'll give you a Spinnaco in a nutshell here. We measure very small changes in neutron velocity using the precession of a spin in the magnetic field. So it's a polarized technique. Have you ever, did we told you that? Because we're using the magnetic moment of the spin, we don't need to monochromatize the beam. So that we can work with a broad bandwidth and still have a very high resolution. We measure the cosine Fourier transform of the spectral function. So the machine does the Fourier transform for us. We don't measure energy, we measure time. We look at time instead of frequency. We are somewhat complementary to small angle scattering, both neutrons and X-ray, because the majority of measurements we do at Spinnaco, they are in the small angle regime. But we do incoherent, I don't know if you guys do it at NIST, we do it at SNS from time to time, incoherent measurements at very high Q. So there, the small angle theory doesn't apply anymore. The drawback, counting intensive, the experiment takes very long. You need to have large samples, you need to have a huge amount of samples, which is unfortunate for the most interesting biological applications. So that's not pleasant, but it's the way it is. Like I said, your spectral energy function, the Fourier transform of that, this is what you get from Spinnaco. It's a function of the resolution in backscattering in any quasi-elastic. The signal that you get is a convolution of your sample signal and instrument resolution. So it makes it a bit tricky to deconvolute because we're in the Fourier transform of that. This convolution becomes a product. So to get the signal from your sample in Spinnaco, you just have to divide by the instrument resolution. That sounds so like nothing when I say it actually means that every time you bring me a sample, and it's the same for them at NIST and for ILL, I would need to mount an elastic resolution and run the exact same measurement that I'm running for your sample and then divide the signal from your sample with the signal from the resolution. If you have a solvent, which most of the time you have, your signal will be sample minus background. The background gets weighted by transmission factor and volume fraction, and then everything gets divided by resolution. That will be the actual I of Q and tau for your sample that will give you information about the dynamical after you subtracted instrument resolution and background contribution from it. The concept of putting a Spinnaco at a pulsating source. So spallation is a pulsating source. Pulsating means that our beam is not continuous. It has a frequency of 60 hertz. We get 160 pulses. Okay? NIST is a reactor, ILL is a reactor. But the concept didn't came from us. Look. It's not my fault. Look at the references again. So they propose it. Ulyss just went for it and built it. Maybe adapted it a little bit, but like I said, it's better for everything. What? This is. Piotr asked me to put this image here. I don't like it. I don't know who these people are except Richter and Schmidt. But then he made me realize this is a key. See this huge thing? is the beamline key. This is from when the instrument was built, I don't know, 2009 or something like that. So this spectrometer has been built by Jülich Research Center and their Jülich Center for Neutron Science in collaboration with Oak Ridge National Lab and Spallation Neutron Source. Until April 2020, it was a German instrument. And then it transitioned to ORNL. Now it's a full ORNL spectrometer with all the rights and the money needed to operate. So now Americans pay for it. It's a high resolution spectrometer. We claim we can detect velocity changes in the orders of 10 to minus 5. No, it's not the only. It's the first spin echo spectrometer at the pulsating source, because I don't want to offend you. It has a spin echo. Oh no, actually yours is at the reactor. What am I saying? Your spin echo is at the reactor, right?
Yes, we have both.
Oh, you have. Okay, so then I'm not the only one. Okay, I'm the first spin echo at the pulsating, but not the only one anymore. But I am the first that I have this spectroscopic design based on superconducting. So look at Bella instrument. Let's be serious. Have you seen the coils? Go to ILS. I'm joking. Superconducting is the way to go. Come on, modern stuff. What? Well, why I'm not using copper coils? Did any of you think of that? Oh, Jesus. Don't wake up this morning. All right. Think about that and let me know later, okay? And then I'll make you first author of the publication like Bella incident a million years ago.
Because it's a pulsating neutron source and doesn't come from...
No, stop. Stop. It's the only spectrometer that has a magnetic shielding, an electromagnetic shielding. So the spectrometer is situated in an enclosure like this. It's a cave. I call it a cave. It's a cave. And everywhere around it and beneath the spectrometer and on the ceiling, there is this new metal shielding that protects us from any magnetic field surrounding electromagnetic variation in the, and I'm telling you, there are plenty of those. The fundamental physics beamline next to us, they are attached a very strong magnets. They have a constant 17 Tesla magnet that is keep pulsating there all the time. I don't see it. I'm pretty sure I will see it, but then I will not be able to do like you guys did with the crane, stop the experiment every time that magnet is on, because that magnet is on all the time. So, yeah. However, I am pretty sure we will remain the only spin echo spectrometer with this type of electromagnetic shielding, because the $3 million that you spend on this are better spent elsewhere. Personal opinion, don't quote me on that. I would have not done it. You could have, but I think it was from the design, there was some German proud engineering into it. Let's do this prototype. Like, it's a prototype. This is a prototype, right? And now I'm operating it like it's a machine that is supposed to run users and produce a million publications and make us all famous. But this has been, in my opinion, has been constructed as a prototype to prove a point. Do not ask me if the point was proved or not. Still working on it. So, there are some differences with, if you compare with Misch's spectrometer. How does he select his wavelength? Do you remember? You show me something. Speak up. Do you have a chopper?
I'm sorry.
Rotating fan. Yeah.
Yes.
The rotating blades that are on a big rotor of some sort is a velocity selector, right?
Using velocities.
Well, because you already know that, I have instead of a velocity selector C1 to C4 here. What do you think they are?
These choppers.
Choppers. Homework. Why do I need choppers? It's easy. Now your answer applies.
Okay, because it's a pulsating.
Yes. Right? What are choppers? Do you have any idea what could be? No? They're just some huge disc, carbon fiber disc. They're just this, seriously. They have an opening, and you rotate it. They're cool. They levitate in magnetic field. That's the cool thing about it. You levitate them in magnetic field, and they spin very fast. And up to some point, their opening gets, we call it in phase, right? So if I want to set a particular wavelength, I will tell it to the chopper. There is an entire software that calculates the speed, the rotation speed. Their frequency is 60 hertz because it has to match the beam frequency, and they will get in phase. Any idea what the chopper is being in phase might mean? Think of it, I will explain it's very simple. This is how some very old Jülich engineer explained it to me, and I thought, my God, this is so smart. Because I was also thinking, they're very complicated in system. Think if I'm on a long, straight driving lane, a street, and I have 4 red street lights. If they're all red, God, I'm doomed. I cannot go. I'm the neutron, right? What does it mean to be in phase? What if they're all green? I would just get my Mustang and right? This is what neutrons do, right? This is what needs the choppers to be in phase, right? The green line, they will select a particular, but only the neutrons because their rotating speed matches. It's calculated based on the neutron wavelength. So if I say give me only the 8 angstrom neutrons, the rotation will match that particular wavelength, and only 8 angstrom neutrons will get through the opening. That's one of the most important differences with tissue spectrometer. Oh yeah, a lot of technical. Oh yeah. One difference is that, which I consider a handicap. So the source, the neutron source is here, the target, right? We extract the beam. This is the shutter. This is where the choppers and the bender and the polarizer sit. Come on. Okay. Another one? No. Yes. So this is my polarizer. That polarizes the beam, and it's also a bender. It bends the beam with 3-point-something degrees, so I don't see the direct beam. And it also acts as a secondary shutter. See how long? I have some pieces of guide here. In my opinion, this is a very poor design. If the spectrometer should be very close to the source. But it's not possible to open the scattering angle here to go to high Qs. It's a wrong location for it, but it's the only one they gave to the Germans when they wanted to build this. We are not served very well by this position. And because of that, the entire spectrometer is lifted on air pads, and it translates on some railway here. And we move it from the 21-meter position, which is closer to the source, to the 27-meter position, so 6 meters ahead. It's an amazing thing to see because it takes all day to do that. I was actually afraid when Todd was my user that he's going to need high scattering angle, and I forgot I'll have to invest an entire day in changing the configuration. My team at SNS, Piotr, everyone here knows him. He's the nicest person in the universe, and I like to call him the lead instrument scientist because he gets very frustrated when I say that he's the lead instrument scientist. I am the so-called point of contact. We used to have this stupid name, point of contact, for every instrument. And the short of it is POC, and I always translated like, I'm the person everybody POCs when something goes wrong. That's why you're a POC. Mary, well, she's the nicest lady in the universe. She always sits between me and Piotr and kind of tempers. As Piotr is chill, I'm always hyper 200%, so someone has to translate this. We're a dream team. This is how the spectrometer looks like. I mean, you've seen their spectrometer, but it's not operational yet. That's why it's so simple. They're just 2 coils, and in reality, it looks something like this. It's a mess of cable and hoses, and I cannot describe it to you. I mean, for my other students that I used to teach in the biology school and in the neutron and X-ray school, I have a movie recorded with the sound of the spectrometer, because if you don't hear it, it takes a lot from it. So it's like a huge pulsating heart. It's so noisy, but it gives you, it gives me peace. When I go down in the cave and I hear the spectrometer, I know all is good in the world, and spin echo is running. It gives you peace. Believe me, it's a meditative noise. Maybe it's a green noise, or because there is this theory about green noises. I'll have to check on that. The beam comes from behind the blue wall. I don't know what they're doing over there. Don't ask me. This is the guy. Here, there is a pi half flipper. There are 2 superconducting magnets, exactly like Mishi is having. Unfortunately, not so fancy that they are going to have. So this is just a prototype of. They got far beyond this. They are amazing. I'm still dreaming. You know, it's my dream. Will I have ever something like that? But yeah. The sample sits here somewhere in the middle. The pi flipper is on this side of the sample, like before the sample. It can be after the sample. You're gonna need to ask Bella why. Because is that ILL is after the sample?
No, but on I-11 it could be before
It
or
could
after.
be before or after, right? So the spin echo magic precession first happened, encoding happens in this magnet, the decoding happens in here. There is another pi half flipper that will bring my polarization on the back on the horizontal. There's an analyzer and the detector where I detect neutrons. And let me know when I'm flippers. They are the same flippers that ILL has and the same flippers that NIST has, but they operate a little bit differently in time-of-flight mode because we're working with the bandwidth of neutrons, so we need to have this ramp. There are too many details for beginning. We have the same correction coil, Pythagoras coils, ILL. You guys have the same. You have the same correction coils, right? I think this is the state-of-the-art in correction coils. That's why people have moved farther with the design of the superconducting elements, because up to now, well, I'll just talk about myself. I'm not smart enough to come with a different design for the correction coils that will correct better. There's kind of the science stop there, so it's best to improve. The way to improve further is to improve on the superconducting elements. The pride and joy, our magnetic enclosure, our electromagnetic shielding gives us a huge stability. Look at the fluctuation of the magnetic fields. There are these 5 sensors around the cave on the outside of the cave. The yellow ones on the inside of the cave. Look how constant the magnetic field at the B sample is. The sensor here at the sample position is. It's supposed to be like that, because if I have huge magnetic variation in the magnetic field at the sample position, that is will count as inhomogeneity. I will lose my polarization, right? So you need to have some field to guide the neutrons, but not strong enough or variations to destroy your polarization. All right. Again, stability over 2 days. Some points of, we didn't measure the line. The points are the measurement. This is just a cosine fit. Over 2 days between the red and it's around 1 degree, less than 1 degree. Phase shift over 7 months, it's about 20 degrees. One phase rotation is actually 45 degrees, so this is less than that. Still, from time to time, it's good to ramp the currents up to maximum current and bring them down to get rid of any hysteresis effect in the wire inhomogeneities that stable enough. We have a mode that I am not sure so far if any other spectrometer uses. We call it shorty. We have this additional pi flippers and some small regular copper coils here. The precession, the whole spin precession actually happens at the sample position well, that's actually shorty 1 with the sample position. Shorty 2, it happens here. The additional flippers, they will stop that precession. Too complicated. The simple thing is why I need this. I can go, so regularly we go from 0.1 nanoseconds, so 100 picoseconds, to 100 something nanosecond, 1 microsecond Bell frames. With the shorty mode, I go in the short Fourier time regime, and that's very good for some polymers and dynamics in, glass forming materials, phase transition, things like that. Especially where you have maybe 2-step relaxations. One of them will always happen at the very short Fourier time. Short, in this case, means that I can go from like 5 picoseconds to 100 picoseconds, right? That is not achievable with the big superconducting coils. You need a different setup for the spectrometer. The equations are here. I'm not going to bother you with this. Bella measures 4 points, 4 phase points to get his echo. Right, to get the maximum amplitude, be able to feed the echo and get the maximum amplitude in the center of phase. Mishi, he explained it to you. How many did we have in the echoes that we feed it? Izzy, how many do we have? 19? 20? 18? 45. Well, don't give me that, because I can also set 100 if I want.
Sorry, I was thinking the degree.
No. The degree is 45, yes. But how many phase points you rate? Okay, 19. So that's is the legacy of Yuli, the 19 points, right? Unfortunately, when you do this technique in time of flight, you kind of need to use many points. Why? Look at this. I have neutrons from 5 to 8 angstrom. So look at, we call this an Atari plot, because it looks like this Atari sign. It used to be an old company with the Atari. The computing people know it, right? But look how my echo, if I group the time of flight, right, differently, and if I get this bandwidth or this wavelength from 7 to 8 angstrom, or the middle one, look how my echo, how the oscillation looks like. If I will measure only 4 points, I might miss my amplitude, right? I might not be on the peak of the, that's the simple explanation. There's more to it, but I need to measure more points. Now, why 19? It's because Monk and Wood, it's a legacy from Yuli. Don't ask me why 19. I'm pretty sure I can go by with 12, but my colleague Piotr, lead instrument scientist, never wanted to put his finger into this problem, so we keep at 19 and move on. Bella, what do you think? We can go less?
You should go to 21, we have 21 students.
Then I will have a reason, right? Well, yeah, but like this, I have 75 in the NX school. Why am I not going with 75?
I wonder.
Okay. Just some technical details. If you run polymers or samples or gels more on the flowing liquid side, we use quartz cells. I think every spectrometer does that. We have different path length here. Niobium cells for high temperature measurement, aluminum top loader, aluminum front loader if you have very viscous sample, rubbers, plastics that they don't flow, you just have to pass them in. Two standard sample environments, a closed cycle refrigerator, and we use this one because it's very stable usually, unless you really need like 500K. Here is how a spin echo, if you haven't seen one in reality, look at this is how a sample, a lipid membrane sample looks like. These are two samples mounted on the holder, and yes, I have the luxury to mount two samples in the same time. Can you imagine that? When I started as instrument scientist, I mount only one sample, and God, I think for the past 3 years I didn't sleep. Because you end up with sample changes that are the most awkward. In one night, I don't know if you have heard this story, but the coyote attacked me at SNS while I was changing sample in the middle of the night. I found out last night too, I didn't know. So that's the sample holder. We are able to mount two samples now, so I can sleep at least a couple of hours more. You put them in, this is the can, the sample can, they go inside this. Yeah, I show it here. We have our own spin echo reduction software, because like I said, Dave cannot handle time of flight. This has been, well, it's a project that has been, for the past 5 years, we've been working on it. We call it Dr. Spiny, and I like to call it a unified reactor spallation software because it's pretty smart. It can handle data from spin echo data, I'm only talking about spin echo data. So raw data from a pulsating source spin echo like mine, but also from a reactor. So unique, this is the twin sister of Mishi's spectrometer. This is how their spectrometer is going to look when it's going to be operational. Except the blue color. I don't know. Did you decide on the color yet? Yeah, well, you. Norm, I think you're going to have to use his logo and put it on the spectrometer. Right?
The blue hat.
The chicken. The yellow chicken.
Yes.
Come on, it's so pretty. You can have a family of chickens. Now, the data that Lizzie, I call her Lizzie because Elizabeth, I have a sister Elizabeth and she's Lizzie, so yeah. Is that okay for you? Sorry.
Absolutely fine.
Lizzie doesn't understand the cube. So the data you get at Mishi spectrometer and at Bella spectrometer, there will be this reactor, one phase, this. The 32 pixel per 32 pixel is your detector, right? Because you have scattering angles, right? Neutrons coming in. You can split this detector in iPad. We still have this. It's a legacy from Yuli. They're called the bi-share rings. And you can use different rings, except maybe the first and the last one, that will give you different cues because they're slightly different scattering angles, right? This is how they get more cues. My neutrons are also coming characterized because they do this for one wavelength. So they get this face of the cube for one wavelength. They say 8 angstrom and they get that. When I say my spectrometer, my job is to set 8 angstrom, they actually do 5 to 8 angstroms. So I have neutrons all the way from 5 to 8 angstroms, right? And I also can tell the spectrometer acquire this in that many channels. I can split that bandwidth as I like. I can split it in 1,000 time channels, or I can split it in, I usually split it in 42 time channels, because otherwise it occupies too much space in there, and it's also very slow. So my third dimension here is the time of flight, wavelength, basically, which comes in 42 time channels. Now, before I saw Antonio's presentation, I thought I'm the most original person on the planet, because I used to explain to students in the neutron school that the TOF data look like an onion. And then your presentation was full of onions. Where did you get that?
I guess.
Oh, you come up with it. Okay, because I come up with it too, but I thought nobody is. All right. So, Lizzie, the easiest way to think of the data is think of a big onion, and then I come with, like, I don't know, metal thingy, and I cut a cube in the onion. If I extract that cube, this is how my spin echo data look like, right? What I mean by time of flight grouping, I start to peel the cube. How do I peel the onion? It has onion petals, and they are petals, they are round, right? So when I group my time of flight, it's not like a straight this, you see? It's like I'll take this onion petal, and this onion petal, and this onion petal. Each time of flight, basically each tiny wavelength, or in reality a bandwidth, because you can split this infinitely, gives me maximum Fourier time and a minimum Q, right? This is how I get my Qs, which here on this is, if you want to measure 0.06 inverse angstrom Q, I will not set 0.06 inverse angstrom, and you might be shocked. Why? Because I don't need it. Because if I set 0.05, I will have all the data between 0.05 and 0.07, right? And then if I need 0.08, I will set 0.07, and I'll have all the data up to 0.1 inverse angstrom, and so on. The data are there as long as you invest in the statistics, because you need to accumulate a lot of neutrons to be able to group all these tiny fractions of neutrons of time of flight together, right? Otherwise, if you don't have enough statistics, you have to group the entire TOF in just one average wavelength, and then if you do that, you end up with data exactly like Michi and Antonio have. But unfortunately, with shorter Fourier time, because your average wavelength is not going to be their wavelength. This is one of the groups that from Gerhard Schneider, has been for a long time. It's a very productive group. We like them because they publish a lot. I had very good students coming from this group. They are experts in dynamics of phospholipid membranes. I've seen a lot. I'm not going to insist. You can read. The name of the publication is here. I'll just go fast through it. This, we already discussed it with everyone in the... I repeated some genius experiment from 1,000,000 years ago. Shame on me. How did I dare to do that? Right? But hey, mine has color. His is black and white, so still some achievement. This is my favorite one, and I will explain you a little bit. This one, because it's different, this is a magnetic material. This is not soft matter anymore. This doesn't flow. And if I put this in spin echo, my polarization is going crazy, right? So this is a permalloy that has this characteristic of a spin high. So the spins are flowing. It has been studied intensively in bulk spin ices, but never in a 2D geometry. So this group has put together a structure like this of a honeycomb, and the magnetic moment, the magnetic charges, they tend to accumulate in the vertices of the honeycomb and flow the defects between the higher integer charges and the lower integer charges. Now, what does it mean? It means that there is a perpetual flow of spin through this. And in the first research we've done on this, we've seen that it actively contributes in enhancing the electrical conductivity of the material. So that's not a small thing, and not only at the low temperatures, like 4 Kelvin, but also somewhere near room temperature, right? Well, science didn't thought this is a great thing, so they pushed us to iScience. But this year we have run a different experiment on that, and it is my favorite. I'm done. This is the last slide. Because it is the first Nature publication of the spin echo spectrometer at SNS. I achieved that. I've done something in my life. Right? Before I went to the spectrometer, no one had any Nature publication. Right? This is my work. Well, no, I'm taking credit for the PI work. He sent me some magnificent students like you that I will ask them do this, and they will do exactly that and not wasting time at the beamline. And we ended up looking at discovering basically that these magnetic charges that they travel through the honeycomb, they are independent of the thickness of the honeycomb element. They still flow regardless of the temperature, even when you go at very low temperature where all the thermodynamics kind of, freezes, and so it's not a thermal fluctuation of any kind. And then we collaborated with a simulation group and tried to characterize these magnetic charges, magnetic particles, with classical mechanic behavior and quasi behavior. And we realized that when you do the classical calculations, you cannot describe the relaxations of these charges. So I am not going to say that we discover experimentally a quantum particle, because if I say that, I will burn on a stick tomorrow. All the physicists will be, I won't get out of this building for sure. But secretly I did. They will realize it in 20 years maybe. My Nobel Prize is still there somewhere, lurking in the shadows. No. So we frame it like this. It was my idea, frame it. No, we did not discover it experimentally. We discovered the existence of a particle, these magnetic charges that they relax. They share a lot of traits and behavior with quasi-particles like magnons. And I'll leave it there with you. Thank you very much.